So we are ready and very excited about the second talk of today. So it's Mickaël Buchet, and the title is "Every ND persistence module is a hyperplane restriction of some indecomposable n+1 D persistence module."
Thank you, Sarah, and thank you for hosting this talk. Thank you, everyone, for being here. This work I'm going to present, I will probably skip quickly over the theoretical part that Arnaud already just covered. And I'm going to talk about hyperplane restriction in multi-persistence and why multi-persistence is going to become more and more complicated when we go beyond two parameters and so on. Let's start with the multi-persistence and hyperplane restrictions. So we're talking about persistence. So the natural idea about persistence is always we start with a equation, we take its homology, it gives us a sequence of vector spaces and linear map. And we can also see that just as a representation of linear quiver. Classical result is that it can be decomposed into intervals, and by what interval is this I, bi, di, and each interval is simply a sequence of 0 vector spaces. At the times b, I get, or index b, I get k, which is a field on with which I'm working here, and then the identity map between k, multiple copies of k until I reach the parameter g, and then 0 afterward. These are all the indecomposable representation in this linear quiver, and there are the building blocks that makes all 1D persistence module, and that's a very strong result that allows us to use persistence diagram, barcodes, and so on. As a shortcut, I will often represent the interval with simply just one line and 2 dots. Again. Just a notational shortcut later, as I will try to be as graphic as possible. So now, multi-persistence, we now have multiple parameters. For example, here, I have a B filtration with 2 parameters, and my sequence of topological spaces is actually covering, varying with 2 parameters. So I have inclusion between my topological spaces, which gives me this, again, linear maps between homological spaces, and everything's commute. The problem with 2D persistence module is that we cannot decompose them into intervals. We can define the notion of intervals, but a lot of persistence modules do not decompose into intervals. There is also no complete discrete invariance. So we do not have a discretely described completely all 2D persistence module, and that's an old result from Carlson and Domrodian from the beginning of persistence. From a quiver point of view, we can say that the representation type of this grid, this 2-dimensional grid, is wide, which means that the number of indecomposable is infinite, and we cannot even parameterize it for a grid sufficiently large. So one idea to study the 2-persistence module will be to restrict it to 1-dimensional affine slices and look at the persistence diagram. It was the first thing that motivated us to look at this problem was the Rivet software from Michael Lesnick and Wright, where they provided a software to visualize the structure of 2-dimensional persistence module using this restriction along one line and various tools that we use. Or, as we just seen with Arnaud's talk, we can do an efficient computation or approximation of the matching distance relying on these slices. And so our first question was, well, if I have an indecomposable module in dimension, 2-dimensional indecomposable persistence module, and I restrict to one line, can I say anything on this line? And we were strongly hoping that, yes, this restriction will have a very specific structure. Intuitively, we hoped, and the problem is when we looked into it, we got a negative result. There is no specific structure because every single 1-dimensional persistence module can be obtained as a restriction along the line of an indecomposable persistence module. And further than that, we can go to higher dimension, and every n-dimensional persistence module can be obtained as a restriction of an n+1 indecomposable persistence. I will give you constructive proof, which is interesting in itself as a construction tool, and some, let's say, fun consequences that might not be far-reaching in terms of consequences, but are nice to look at. So first, let's formally look at restriction. If I look at what Arno just presented, we take a line, an affine line, and we just look at this line and this red part as a 1D restriction. Actually, in the way we define it, the restriction, we can make it a little bit different. We do not necessarily need it to be an affine line. We just need it to be a non-decreasing line with respect to the order on the parameter space. If I look at hyperplane restriction, it's the same thing. I'm not looking at a line. I'm looking at, if I have an n-dimensional persistence module, I'm looking at an n-1 hyperplane with a contour which is non-increasing. Actually, let's keep it simple. And for my talk, I only need horizontal lines. I don't care about anything else. And all my embedding of n-dimensional persistence module into indecomposable n+1 dimensional persistence module can be done along a line or along a plane that is horizontal with respect to the last coordinate. So a few important points. Due to a definition, I'm saying that one module is a restriction of another one, and that's considered up to 2 stations. I don't care where I move to the grid. I will assume that the grid is infinite. But all modules I will consider, unless mentioned otherwise, would be finite. And it's up to isomorphism. So if the restriction I'm looking at, and I have another restriction, and I have another module which is isomorphic to it, but not identical, I will still say that it's a restriction to the given module. And our theorem is that every finite n-dimensional persistence module is a hyperplane restriction of finite indecomposable n+1D. So let's start by making the construction for 2D. So I'm going to take a 1D persistence module, and I will build a 2D indecomposable persistence module. When is a persistence module indecomposable? Well, one characterization is to say that it's endomorphically local. Now, what is a local ring? It's just that every element of this ring is either invertible or 1 minus this element is also invertible. Fortunately, you can forget everything about it and just look at one consequence is, if the endomorphism ring of a persistent module is isomorphic to the field K I'm working with, then it is indecomposable. And I will only use this property to prove that my constructions are indecomposable. So let's first look at 1D interval. Well, that's nice because that would be a good warm-up, and we already know that they are indecomposable. So here I have one interval, and I copy it, and I look at all the automorphism I can build from this interval to this interval. That means that for every vector spaces here, I need to find a map that map it to its copy, its second copy. And of course, I also need everything to commute. Well, if I look at F1, F2, F3, F4, F5, they are all linear maps. I need to define them. Fortunately, F1 and F5 are easy. It's a map from 0 vector spaces to 0 vector spaces. It's 0. The second one is, well, F2, it's a map from K to K. I can just define it by a scalar alpha. And that just fixes my map. Now, I can look at F3 and F4, and because everything has to commute, F3 and F4 also should be the same map defined by the scalar alpha. You can just see that alpha is the value to which we send the unit element. So that means that for my interval, its endomorphism ring is any element from its endomorphism ring is fully determined by one element of the field K. So it's local, and this is indecomposable. Can I now look at morphism between intervals? So let's not look at endomorphism, but if I have one interval that has another interval, can I do it? Well, if I decide to replace this K by a 0, that implies that my map alpha now has to be 0. So I can replace it. I check that everything's commute. And yes, this is a map that is potentially non-zero if alpha is non-zero, that go from this interval to another interval. On the other hand, if, for example, I decide to work with this one, this vector spaces to become 0, now I also have this map, which is a problem, and I need to put it to 0. But now, because of the commutativity of this square, this map alpha here also needs to become 0. So if I take this interval, let's say it's 1 to 3, and this interval, which is 2 to 2, then I cannot build a non-zero morphism between these two intervals. And that will be an important tool. Actually, we can make it a theorem that if two intervals AB and CD, and I look at the morphisms that go from AB to CD, they only exist if C is less than A, is less than D, is less than B. And I have a canonical morphism that I can use. That just says that I put alpha equal 1, a unit element from my field, and then I define this element. And now I know that all morphism will be of the form K, one element of K, times this canonical morphism. If this C less than A less than D less than B is not condition is not satisfied, then my morphism is necessarily 0. That allows us to use what we call the matrix formalism, which means that when we look at a 1D persistence module, and we take its decomposition into interval, and we look at a second 1D persistence module that we also look at its decomposition into interval, we can write any map phi that goes from one to the other. This morphism, we can write it as a matrix, which is a shortcut to say that, well, we take in this direct sum, we look element by element, and we just take a coefficient times the canonical map that maps from this interval to this interval. This canonical map between non-zero only when the condition, this condition is satisfied. Otherwise, this is 0. The important thing is this is a shortcut. You should, in all matrices I will write, you should not forget that there is this map. It's here. It's not returned, but it's here. So now let's look at one special case, and let's look at vertical intervals. So now I'm just saying that I'm going to take intervals, and the support of each interval is included into the next one. And I'm taking a module which is the direct sum of this interval. What is the endomorphism ring of M? Well, here are my three, for example, my three intervals. And we see we have a very big one that's into it, another one that's into it. And the thing is, by the condition I had before, I cannot have a non-zero morphism going from from the middle interval to the top one, and I cannot have one from the bottom to the middle one, or from the bottom to the top one. So that means that my endomorphism between endomorphism over M has to be diagonal. Namely, I can only map this interval to itself, the middle one to itself, and the top one to itself. So I can write the matrix as being a diagonal matrix with coefficient C1 to Cm. I have M intervals, and 0 everywhere else. That's very interesting because now I can look at 2D persistence module as stacking 1D persistence module upon each other. So I have a 1D persistence module, which is a direct sum of this swift interval. I pick a second one, let's put it just one interval. And now the only thing I need to define my 2D persistence module is to define which map I should put in between these two modules. And for example, here, let's put 1, 1, 1. I carefully chose my interval on the top so that I can put it, I can have a non-zero map for every one of them. Of course, this 1, 1, 1, again, that's not the identity. Every one of this one is actually one time the canonical map for the first one from the top interval here to this interval, from this interval to this one, and from this interval to this one. That's my three canonical map. Let's look at the endomorphism ring. Well, this is an interval, and we know that its endomorphism is K. So if I have an endomorphism, I have to be alpha. Now, at the bottom one, we just saw that it has to be a diagonal element, C1, C2, C3. But because I'm looking at an endomorphism of this as a 2D persistence module, I now need to commute with this map I built here. And if I enforce this commutativity, then C1, C2, and C3 have to be alpha. And again, every endomorphism on this 2D persistence module has to be is fully determined by one scalar element. Okay. So that means that this module, 2D module I just built, is definitely indecomposable. So I just solved my problem for the very specific case of this vertical module. Now, let's do it for any module. And we're going to transform this sequence, this direct sum of intervals, into a vertical one so that we can glue this construction on top of it. The first thing we do is we decrease the burst time of all intervals. And that allows us to have a map, 1, 1, 1, for example. We fix it to be this one, because when we move the burst time to the left, then we can have a non-zero map going from this interval to this interval. I can just build this. Then I'm going to reduce the death time here. And same thing, when I reduce the death time, I can also have a non-zero map. So I can also put the 1, 1, 1, 0 here. And now this is a vertical set of intervals. They are all into each other. And I can just do the same construction, which is to take the one which is as a minimum burst, the minimum death, and put 1, 1, 1. And I get a 2D persistence module. Now, what is its endomorphism ring? Well, we just did the computation before, and now I'm looking at this one, and I don't know, it can be anything. Well, I multiply this matrix by this matrix, and I'm happy I have alpha everywhere. Well, that's going a bit fast because there is a trap here. It's true it works, but you have to be careful because this is a multiplication of matrices, but the matrices contains elements which are morphism. And the trap is that if I have two elements of K on my field K and I have beta times alpha equals 0, well, then necessarily I have beta equals 0 or alpha equals 0. But now I'm looking at beta times the morphism composed with alpha times the morphism. And this is 0 if beta is 0, alpha is 0, or if the composition of the two maps is 0. So I don't have much time, so I'm going to put that under the carpet and tell you this case never happens in the relevant places where we need to be able to show that this has to be a diagonal matrix alpha. And so this gives us our theorem that for every 1D persistent module, there exists a 2D indecomposable module that contains it as a line restriction. My whole construction was named Primal construction. One of the consequences is that I can also do a dual construction. And what I do is that previously I was mapping by moving the burst to the left, the first time to the left, I was mapping it. Well, let's just move the death to the right. And now I'm going to map it down. Well, so actually I cannot map to it, but I can map from it. So I get this set of intervals here. And now instead of moving the death to the left, I'm going to move the burst to the right. And I get the exact same thing and the same construction. And then I can just link it with this time the maximum burst death, and same result holds. This endomorphism is also K, and this is an indecomposable. And I can actually glue them together. And for example, I have this very wonderful list of the persistence module. And that's one of the consequences we can show. And it's interesting is that if I start with this middle line here, which is just a direct sum of two very small intervals, then I build everything up, the primal construction, the dual construction in the middle, at the bottom. And now I have this 2D indecomposable module whose support contains a whole. So I have 2D indecomposable module whose support does not have a trivial homology. And actually, I can very quickly choose any n, and I can find a finite 2D persistence module whose support contains n whole. And a nice other result is all my modules have this structure. I have the module I start with V here, and then I build this staircase shape around it. And we call it a candy module because you have a vector spaces on the top left, which is K, at the bottom right, it's K. Its isomorphism is isomorphic K. And so in some sense, we have wrapped V like a candy into a nice thing with two little handles, and we can do something funny, which is glue them together. You move one here, you add a vector field K here, two maps which are just the identity map between K and itself, and now you string them together, and you can string as many as you want if you are in an infinite graph. Great. And this one is still indecomposable. And I can just enumerate all finite 1D persistence module, and then I glue my construction for every one of them all along here. And I get a 0.5 finite dimensional 2D persistence module, which is infinite, but contains all of 1D persistence module as line restriction. Of course, up to isomorphism and translation. So now that's a nice construction. Can we extend it to higher dimension? One problem is that it's not as easy. The easy case is a rectangle decomposable. So a rectangle module is just a module which is defined as a product of intervals. And you can just look at each dimension independently, use the previous construction, use the product operation smartly, and then you get that every finite rectangle decomposable ND module is a hyperplane restriction of an indecomposable n+1 D module. The consequence is, I was talking about non-trivial topology, I can actually fix my Betti number of 1 to n, and you can find in the module will support the number of 1 n, and that's easy to build using this rectangle decomposable. Going a bit fast, but I'm almost out of time, so let's go over quickly. I have a projective module, which is the same as free module or injective modules. They are rectangle module, but they are not finite on an infinite grid. But one important thing is that every persistence module has a projective cover and an injective envelope. So I can find a canonical way to have this projective module, but this direct sum of projective modules, which are rectangle modules. This is the rectangle decomposable. I have an injective here, which is also rectangle decomposable. And I can just use my construction on P, the primal one, the dual one on P, the primal on I, and then I will have what I want. Unfortunately, I and P are infinite, so I first need to restrict myself to a finite right containing n, take the projective cover and injective all, build indecomposable using P or I as a starting point, do everything together. So I get this sequence of ND persistence module, which here is my previous construction with P as a starting point, the dual construction. Here is I with the primal construction, M in the middle. And I ask you to trust me, to trust my word on that. This whole construction gives you an indecomposable. So now for any M here, I have an indecomposable n+1 D persistence module that contains it as an hyperplane restriction, really the horizontal one. Same trick as before, I can just go and string them together. And I'm happy, I'm saying, okay, it's going the way. Well, not exactly. I need the field K to be countable to be able to enumerate all my ND persistence, finite persistence module. And so for n larger than 2, this big beast, this overload that contains all other representation, as well, to exist, we do need it to the field K to be countable. That's not a very huge restriction. So I hope that this kind of interesting construction you find fun, at least I do, and it has some interesting consequences. The whole complexity of the ND persistence module and finite ND persistence module is actually contained just in the indecomposable of the n+1 persistence module. If the field K is countable, I can even say that the whole complexity of the ND persistence module is just in one indecomposable of this module. So that's a bad news for computer scientists. That means that any method we could find to deal with bifiltration. Well, what did I say? Okay, there is a negation here, sorry, will not translate easily to higher dimensional parameter spaces without important dimensions. Because the complexity, we have a gap, a huge gap in complexity every time we add one parameter. Okay. Thank you for listening, and if you have any question, I will be happy to answer it. Hopefully it was not fast.
Okay, thank you. So before we get to questions, please unmute yourself and so that we can clap for Mickaël and his wonderful talk. And now it's time for questions. So just to double check, Ira, do you want to ask a question? I hear some noise coming.
No, me? Did I make noise?
Ah, okay, yeah.
No,
well,
I just applauded. Sorry.
Okay, very good. So yeah, so if whoever else has questions, feel free to unmute yourselves and ask, or type it into the chat window.
Hello, I'm Ujin. Thank you for a nice talk. I was wondering what kind of future work you're considering in this direction of work, if you have something in mind.
We had some ideas, but I don't know if it's actually useful to anything. So one question, maybe not that interesting, but our construction is very space consuming. When we build it, like, okay, if I go back to the one I call the beast, right, this huge thing, this is the result of our construction right now. You can make a whole is a much smaller module. Really, we also showed that the minimum contains only 11 vertices. Is there a general way to make it smaller? Yes. One question would be, what is the smallest way to, like, how small can the 2D persistence module be, or n+1D persistence module be? Here, I'm stacking at least 3 lines on top of my module to make my construction. Can I do it with 1? Can I do it with 2? I don't know. That's one question. Another way is, the way we look at restriction right now is by saying that we take an injection in some sense. We look at the module as a submodule along a line. That's one way to look. Another way to look at it will be to look at it as a projection, which means that I'm looking at the direct sum. If I have multiple modules like this, I'm looking at the direct sum of these modules as one line. In this case, is it possible to have everything or not? That we don't know. Probably not, because if you do it, you will have everything to be connected. So the class of module you can obtain will be smaller. But it is exactly, is it all connected module? I don't know.
Thank you.
Okay, so we do have another question in the chat window. So in the 2-parameter case, suppose that we have a finite family of lines, L1 through LD, and for each line a persistence barcode PI. Is it possible to find the 2-parameter persistence module which lives them, or are there some interesting compatibilities that must be satisfied? Thanks.
So, sorry, I try to understand exactly. So you have L1 to Ln, which are different lines?
And for each line, a persistence barcode PI.
Yes. Okay.
Is it possible to find a 2-parameter persistence module which lives them?
So it depends how you define lines. That's the tricky part. If the line you define, you fix them as, sorry, I'm going back so I can explain. If I fix my lane, I said I want this one, and then I want this one, which is 0, and I do not allow anything in between. Like I cannot start saying, oh, I'm saying I want this line, and I'm not looking at up to translation. Then you have some incompatibilities that will come into play. If otherwise you are free to place it a bit like you want, well, you can do it. I do believe there are some incompatibilities that will not allow you if you give me a finite grid and you tell me, okay, this line should have this persistence module, this line should have this persistence module, and the whole thing, when I glue it together, has to be decomposable, then I can provide counterexample where it's not possible. One easy way to look at it is, well, actually, it's here. Right? If I decide that I take just a grid with just 2 lines, and I said the first line has to have some things that go from 2 to 4, and the second one has to go from 3 to 3, then you cannot have a non-zero map in between. So this 2D persistence module, which is exactly the one you are forcing to be, has to be decomposable. Because you can decompose it as the direct sum of the first line and the second line.